All right, as we near the end of the class, one of the critical things we need to talk about is creating and managing larger software projects. Key to this is the software lifecycle, and I'll talk about that in a minute. It's down here. It includes these different steps: investigation, design, implementation, testing, and maintenance. And the problem here is if you don't implement a minimum amount of work in each of these steps, your project will fail. And that's critical. The reason that's important is because 90% of all software projects are late and 50% never finish. There's a number of reasons for this. One is the inherent nature of developers. A lot of software developers like computers. They like playing on computers. They like looking at new technology. Well, that allows us to get distracted and go off and do all kinds of different things that may not actually be what the customer wants. We have to focus on what the customer, I should have said, needs. That's the really key thing. Focus on what they need rather than what you want to develop. Now, the way to do that is listen to your users. As a developer, you will quickly become corrupted and think things are important that aren't important to your user. Now, when I'm talking about larger software projects, I'm talking about when you may end up in a situation where you're in a large GIS software group, such as with the USGS, or even actually if you work for someone like Caltrans and you may be the only developer in the office, but we've got some alumni who are the software development group for an office. And so they're spending a lot of time writing software for other people to run. If you're the user, it's a lot easier to stay close to the user, but you may still even miss what it is you really need. You always want to be thinking about what do you need, focus on that, and make sure that is done well. That will help you be successful. Very true also with reusable modules. Make sure to remember that you're one of the customers, but down the road, other people may be using it. And so you want to build those so that other developers can use them. Another big reason that software projects fail or are late is because of feature creep. And this is where you've got the project up and running, software up and running, you show it to someone and they go, oh, that's really cool. Wait, add this, and let's add this, and why doesn't it work this way? And all of a sudden, you're spending tons of time adding one feature after the other. And you're adding it on top of a piece of software that isn't well tested or documented. So not only will this cause the software to never be done, but over time the software can become unmanageable, ridden with defects, poorly designed, and you just have to give up. So you need to push back on feature creep. The best model I've seen for this is the train is leaving the station. This comes from Dean Buck, one of my mentors at Hewlett Packard, and the metaphor he used was to say, look, we're building this piece of software, it's a train, it's at the station, it's going to leave, it needs to leave, we got to get it out the station. But there's going to be another train coming. So when folks come with new features, look at them and say, well, does that go in this software or does it go in the next version? And if it goes in the next version, create a list, put it on that list. And then people say, oh, okay, we're going to get this feature, but it's in the next train. You get one train out, it's well tested, well documented, you've got a solid base of code, the next one comes into the station and you start working on it. Another key is communication, again, particularly between the user of the software and the developers. This is a famous cartoon from Alan Chapman that summarizes this. It not only shows what happens as far as miscommunication and what's going on with the software, but also often the customer needs something that is much simpler than what anyone in the organization might be envisioning. And so again, if you focus on the customer, you may find yourself spending a lot less time having to get the software done, and more importantly, a lot less frustrated because you've finished it on time and you've shipped it and the customer's using it and they're happy with it, rather than being really frustrated and everyone looking at you that you're not done yet. Another common problem is represented by the book, The Mythical Man Month. They should rename that, of course, the Mythical Developer Month or something. But basically, if you get to the end of a project and it's late, folks tend to say, oh, let's put more people on it. And as soon as you put more people on it, you have to bring them up to speed. There's more communication issues and everything falls apart. And so it actually causes the schedule to slip if you add people to a project at the end. My strategy here is panic up front. In other words, panic at the start of the project when you have time to get additional resources and get them up to speed. You have time to get stuff up and running, investigate different technologies. panic up front, get started up front. It also gets you to focus again on what's needed, make sure you get that core software done, and then as you get near the end of the project, you can relax, make sure the testing is there, make sure the documentation there, make sure that the finishing touches are really done on it, and it's great and ready to go. All right, quick overview of the different phases. Investigation, critical, and what's critical here is getting those requirements from the user for what it really needs to do. Design is how you're going to construct the software. We'll talk about that in more detail. Implementation is where you actually write it. Testing, of course, testing it, but also fixing the defects that are found in the software, and then maintaining it. And down here I have what we created at Hewlett-Packard, Rick Lesser and I especially, and this is a model where we recognize that there's these phases, and in the industry there's something called the waterfall model where you finish investigation, then go on to design, and then finish design, go on to implementation. There's also a model where you just cycle on all of these all the time. We found none of those really worked optimally. We found it was better to recognize that, well, you're doing investigation, and while you're doing investigation, you can start doing design. And then you start doing implementation. But especially in implementation, you may then find something in the design that doesn't work. There's a performance problem or complexities. So you need to go back and rework the design. And then you go back into implementation. And then as you implement, you test. And in testing, you may find, uh-oh, that didn't work as well. We need to go back to implementation, maybe back to design. But you don't want to go all the way back to investigation. You want to keep moving forward. And then maintenance, as soon as you have folks start using it, they're going to test it as well. That results in potentially changes to implementation. And also, of course, maintenance keeps going. And then if you do large projects, they'll tend to take quite a while to develop. And so these can overlap. While you're maintaining and even testing one product, you could start the investigation cycle for the next project. And on it goes. Now, in the modern world, especially with web development, we tend to just cycle on this continually. We used to run this once a month at Colorado State. And you could do it on a weekly basis for smaller websites and just be, constantly running this life cycle. It is important to do it and to continually update the documentation. Another factor to consider is the user needs. I worked initially in production. This means we shipped over 1 million software products, so the quality would be very high. If the customer returned the product, we lost money, so that was really important. Number of users, lots, over 1 million. What's important with the technology is what works. Short-term learning curve. If they don't get it out of the box and get it working and are happy with it, they're going to return it. Had to have support, of course, and the documentation has to be complete and very easy to understand. If usually they won't even go to the documentation, but for those who do, got to be able to get to it quickly, figure out what they need, or again, they're going to return it. Because the bottom line is if it doesn't work, they're going to go elsewhere. Now, research is a little different. So if you're in the research community, the quality, it needs to be accurate. That's more important. It could have a few bugs and they'll deal with that. But if it produces the wrong output, that's not going to go well. Smaller number of users, which means that the learning curve can be longer. The support, basically, yeah, we have chat groups that we use. The technology can be the latest and greatest. And again, doesn't work perfectly, they'll be, okay with that. Somewhat. They'll get annoyed, but they still will use it if it gives them what they need. Documentation can be less and techy. Again, they'll email you, so it's good to have some documentation. And the bottom line is if it's cool, if it does what they want it to do and it's the neat research stuff they're looking for, they will use your software. Now, the GIS world runs the gamut from here. Of course, products like ArcGIS, QGIS sit on the production side. There's a lot of tools like in R that are definitely on the research side, and a whole gamut between, and you'll probably be producing something somewhere along this gamut. So it changes what's important for the user needs. Okay, quickly with investigation, the important deliverables here is the requirements document. Okay, so that's absolutely key because what's in it is the main features. You want to really focus on those. What is it the software is going to do for the user that's going to meet their need? Which platform, which GIS package is going to work with? Performance requirements. How fast does it have to be? How reliable does it have to be? Does it work on all file formats or is it okay to only work on a few? So very important to get these clear. It guides the development, but it also sets the expectation of your, not only your customer, your clients, people are going to use it, but also of your superiors. You can let them know, hey, this is going to work with ArcGIS, but it's not going to work with QGIS. So people need to know that, or it's only going to work with TIFF file formats, not the 120 odd file formats we have in the GIS world. So very important to set their expectations for your success. Feasibility studies are where you go off and investigate things and say, hey, is this going to work? Now, where I tend to have schedule issues is when I assume that a library is going to work, especially in Python, and then I start using it. That didn't work, or it crashes or breaks, runs too slow, all kinds of problems with libraries. So you need to really make sure those libraries do what you need, because if they don't, you're going to have to write it, and that's going to take more time. Schedule, very important with those phases, the budget, and then the other resources. And don't forget all the other resources, the data you may need, other libraries, anything you may have to pay for, etc. Okay, a few different tools. Use cases are a method to make sure you're taking the user's perspective, and this is where you identify people as agents and say, this person's going to use the software. And you can even name them. In fact, it's really good if you know some folks from using the software, use their name and say, okay, now what are they going to have to do? Well, they're going to have to do things like install it. Then they may be determine the area of a watershed behind a dam, common problem. Running the tool with a DEM doesn't overlap with a selected dam. That could be a problem, so you want to make sure that's in your use cases. These then turn into your test scripts that I'll talk about in a second. Okay, onward to design. So design is something that nowadays, especially with projects that start small, which is most of the ones I work on, we don't do a whole lot up front. We used to do a lot more. You want to do as much as you can, but the bottom line is we don't really know what the design is going to look like until we start building the software. So as we build it, we will then begin designing the software. And most of the projects I work on, the really important diagrams are hierarchy diagrams that show the structure of the classes within the software. If you have large data processing projects, you want to show the data flow. If you're doing control software, like for remote controllers or data loggers, the control flows. If you're doing something that has a lot of GUI to it, a lot of graphical interface, then the user flow may be critical. And there's a lot of documentation on how to develop these, and a whole wealth. In fact, you can get a degree in software design. Go ahead and spend as much time on that as you need to. As your project gets bigger, you have to spend more time on the design so that the software stays nice structurally, so you can keep moving forward and adding things and testing it well. Now, by the end of this phase, you also need to have selected your development environment, locked in on which one you want. Source code control system, also critical. Defect tracking system, we'll talk about that in a second, and test management. The user interface is one of the keys, especially nowadays with a lot of the small applications, tools in Esri. And again, you'll have limitations with those. You want to make sure the user can use it. That is another entire discipline you can do. We've talked about a little bit before. I'll hit it again. One of the things that I tend to do, especially in Python, where I tend to just start writing code, and then I'll keep adding and adding and adding, is then we're going to be redesigning on the fly. You do want to do design documentation as your project gets more complicated, but you can do design on the fly. And basically, you start writing a script, and then as you're writing it, you start to find duplicate code inside your script. So you move that into a function. Then you get a bunch of functions, and especially when they start being related, like you find, oh, I've got a bunch of conversion stuff. Well, those are good to move into a module. And then if you start to see that your modules are sharing the same variables, they're using the same data, that tends to be key to say, oh, I need to convert this module or this group of functions into a class, and then they can share their data, and that can be encapsulated within a class that you can then call. Now, if you're doing something like agent-based modeling that we talked about, or a large project that has a big GUI in it, you will want to do some of this design ahead of time to get the structure in place. But most of the stuff we do in GIS grows over time, and so you can do this as you go. And definitely do it and reorganize it over time, or things will get very messy. Okay, Implementation. Well, this is where you write the code. This is the stuff we tend to be good at because this is what we tend to focus on. By the time you're done, you've not only got executable code, but also installers for it, whatever you need to do for installation, and you should have documentation. In other words, you want to be writing the implementation document, the documentation during the implementation. Now, the reason for that is because you're close to the code. You know what it's going to do and what it's not. So this isn't perfect documentation for the user. This is the start of that, and it contains those key things where it's like, oh, this file format doesn't support this raster data type. Bummer. Well, that needs to come out in the user documentation, so you want to make notes about those. Now, the other thing is it also focuses on getting it done. You've got to get it done quickly. You do want to have defect tracking on while you're implementing. We'll talk about that in a second. And you want to look at debugging strategies. In fact, I spend a lot of time looking at my code saying, how can I build in debugging code to help me debug my software as I build it? So you don't end up in a situation where it's like, oh, we need to debug this, but the code that we need to debug is 20 layers down inside and really difficult to debug. We see this mostly with web services on the web, where web services are very difficult to debug, especially if they're chained through 3 or 4. I once debugged a web service through email. That was interesting. Not the way I would want to do it. So you just want to think about it. And of course, keep your code easy to read, well documented, keep it as simple as you can. Those will help you in debugging. All right, testing. So a couple things with testing. You want to have test scripts. And there's different ways to manage your test scripts. I often start with an Excel spreadsheet and just have a list of tests that I need to do. Some of these can be automated. If you can automate them, great, do it. If you have a GUI heavy product, then you're not going to be able to automate most of it. You're going to have to do it manually, or if you have a large project, have someone that tests it for you, all the better. Okay, basic user tests are the core tests that you want to run every time you produce a new version. Make sure it works. And then as your software becomes more complex, we can't test every possible combination of using features. So we do what's called sparse matrix testing. We hit the broad array of features, but not every single one. Robustness, a lot of things like web services, or if you're going to download data, if you're going to process data and you're going to process 10,000 files, it's got to work. It can't overrun memory. It can't run out of disk space. You know, all those problems come out when you just put your software in a loop and you run it 10,000 times. And then random tests are also good. Just throw random data at your software and see what happens. So different types of test scripts. And there are systems for managing test scripts, but again, Excel works fine for smaller ones, and then you can go to a complete database if you need to for a large project. Defect tracking system, absolutely critical to have a defect tracking system. Again, this can be an Excel spreadsheet to start, where you record your defect, what happened, how did it break, and then you move it through a series of stages. So new is when it was first found, confirm to say, yep, we figured out the defect. And you have to be careful at each stage, because sometimes a user will say, oh, here's a defect, and the developer go, oh yeah, we fixed that. And the developer hasn't even really looked at the defect. Developers, most of us, do not actually like fixing defects. So you need to make sure that the defect that's found is the one that's confirmed and fixed. Now, some defects are duplicates, but again, you need to confirm. Sometimes they're not a defect. That doesn't happen as often as people think, because even if the user went through the installation instructions, they couldn't install the software, and the instructions were wrong, well, that's still a defect. And you want to treat that as a defect and go back and fix the documentation just as you would the software. Otherwise, that could get lost, and we don't want to do that. We don't want to lose defects. And then resolve. Resolve says, yep, it's done. Now, the best person to resolve the defect is the person who found it, because they know what the defect was. So typically, we produce another version of software. They go back through the defects that they own, and that they created, and they make sure that they're all fixed, and off we go on to the next round of testing and defects. And that cycle just repeats over and over and over again until your defects are down to a level where it's okay to release the product. Now, when you release it, very important to have training and documentation. Okay, so a lot of things that folks miss, how to install the software is huge, and you as a developer do not have the perspective of the user. You may be going through 10 steps to install something and you've forgotten 5 of them because you just do them automatically. So you definitely want to test the documentation as well. Versions of software. The ArcGIS tools only work on a specific version of ArcGIS. So that's really annoying, and you may have to do different versions. How to get started, absolutely critical. We tend to use a lot of web pages now for this, but a README can work if you have a small script. And then known defects. In other words, let the user know what defects you already have. In fact, you could just make your defect list available to them and say, here's the defects. Be open about it. Let them know there's defects there so that they don't get frustrated. Instead, they go, oh, okay, we'll just wait until that gets fixed in the next version. Everything needs to have some level of user's guide, tutorials. Again, this will vary quite a bit. But also important in the release process is to let folks know how to give you feedback and make sure that loop is there. So if they find a defect, they find a problem, you hear about it quickly and fix it quickly. With small projects and you're in the same office, let them know, and often you can get it done even the same day. Otherwise, let them know it's going on the defect list and you're going to fix it. Now, the thing about the maintenance cycle is as soon as you write something and you give it to someone else, it never goes away. Okay, it will keep coming back, often haunting you. And so you want to have it on your list as something that you're supporting. If you change jobs, you need to let folks know, hey, I'm transferring this to this person. Okay, it only really goes away when everyone stops using it. And that doesn't happen as often as you might think. So have a good time building big software projects.